So so good morning, good afternoon. It's you are at the end of these 2 weeks of seminars and lectures. So you are an expert of gravitational waves, right? So what I can do in this talk is to try to pick up a particular stochastic background and to explain and discuss the broader approach to it, not only gravitational waves, but also how this problem is embedded in many research lines in physics. As Danny explained yesterday and the day before, the studying gravitational waves is interesting for several reasons. But at least for me, that I'm mostly a cosmologist, the most appealing aspect is that gravitational waves interact very feebly. So what you can do is that you have a source of gravitational wave in the very early universe. And since the coupling, gravitational coupling is very weak, this wave, this signal, will not scatter many times before reaching us. And this means that the information that is contained in the gravitational wave about the source will reach us practically uncontaminated. And why do we care about this aspect? Well, the main point is that we don't have direct access to what happened in the universe before the CMB, because the CMB is a barrier to photons, and a photon produced before the CMB scattered many times before reaching us. And this means that basically it loses the information of the source. So what you can do is just to have statistical measurements on the photons, but you don't have the direct access of the sources that produce those photons. And what do we know? What do we know? Okay, what do we know?
Yeah, you have to click on the slide in general and then it will.
Okay. And what do we know about the early universe? Well, I said we don't have direct access to the early universe by means of photons. You have neutrinos, but they're very weak, so you're not able to measure them. And but you have a way to probe a part of the universe, at least the particle, the matter content, the particles. And for that, you have some experiments, colliders, typically, particle physics experiments. And as you can see here, right, this is roughly the energy scale that you can probe by means of colliders. Notice the scale is GV, the units, so 100 GV, 1 TeV. But this is not completely satisfactory, right? Because here, what you're probing by means of collider is the particle content, but you're not probing the general conditions. For instance, it's very hard to probe the finite temperature condition of the early universe and the fact that at the time it's expanding. So, for instance, a general question, do you believe that at this scale, let's say at 100 GeV, the universe is radiation dominated? Do you know if we are very sure that the universe is dominated by radiation this epoch? And the answer, okay, it's difficult to interact, but the answer is not. You take a cosmological model based on what you can measure here, and also by inferring something that happened at the beginning, and you extrapolate. But of course, there is room for changes. For instance, you might have that the universe that at this epoch is not radiation dominated by, but is dominated by other form of energies. And of course, this, knowing that, has very weak effect at the end, but of course, change completely our comprehension of the early universe. So, what kind of gravitational signal do we expect from the early universe? Well, as Danny explained, it's a stochastic background. So what are the sources of stochastic background? Well, unfortunately, it's not only the very early universe processes. You have also that gravitation late time sources when you're not able to resolve well them, they produce a stochastic background. Depending on your community, you call this a stochastic background or foreground. So the stochastic background, when you measure that, it will be a mixture of late time sources that you are not able to resolve and the signal from the early universe. Traditionally, you measure the signal or the energy, the quantity that you can measure of the signal in terms of omega, that is the energy power spectrum. And what really matters here is that there is, well, it's not so explicit, but there is a frequency dependence. So if you're able to measure omega as a function of frequency, you can achieve a lot of information about the sources. We will see that later on. So just focusing on Lisa, because I know just a bit more. What kind of backgrounds do you expect? Background foregrounds? Well, in Lisa, you have many foregrounds, and because there are the galactic binaries. Galactic binaries are so many that you cannot resolve. Many of them you can resolve individually. And there is a characteristic that is crucial for them, that they are galactic, so they are in our galaxy. And this means that these sources are aligned along the galactic disk. And this means that when you measure the background produced by them, this background is not isotropic. You have the stellar origin black holes, which are many. From LIGO and Virgo measurement, we know that now the population is very abundant, and the signal that it's so abundant that many sources will be not resolvable in Lisa, so they provide a foreground. And moreover, in general, you should care about all the sources, astrophysical sources. In principle, you might have that the neutron star binary produce a foreground, the Henri, the extreme mass reaction spirals produce a foreground, and in general, the binary populations. But okay, you had many lectures about that. So let's move a bit more about cosmology. Danny covered that, but just let me remind that you have broad classes of mechanisms that produce in the early universe a stochastic background. You have inflation, you have cosmic strings, you have primordial black holes, superradiance. Okay, these are not very early universe, but they are for a stochastic background, let's say, connected to beyond the standard astrophysics. And you have a cosmological first-order phase transition. And in the rest of this chart here, I'm focusing about this signal, this source, the first-order phase transition. But in general, what most of the things I will say applies also to the other sources of the early universe. So the technicalities are related to this particular source, the first-order phase transition, but the general message applies to all the early universe stochastic backgrounds. Yeah, if you have questions, please interrupt me whenever you wish, even without going through the chat. So the main questions of this talk are the following. Why we expect to have a first-order phase transition, at least historically? What is a first-order phase transition? And what is the signature? We know that it's stochastic background, but we have more details about that. And moreover, as I gave some hints at the beginning, it's connected to the particle content of the universe. And so we will have collider signatures. And in general, it's very nice to speculate or to make predictions about the early universe. But in the end, what matters is to be able to test them. And so the crucial question is this signal detectable at Lisa? In particular, at the level that you can recognize if the stochastic background that you measure is coming from a first order phase transition or something else. So this is the outline. So why historically do we want a first order? Did we want a first order phase transition? Here the audience is quite young, so you can check that in Inspired by checking electroweak phase transition or similar titles. You will see that the investigations about the first order phase transition are before you starting being a physicist. They're old, even before I became a physicist. Okay, so there is a crucial question in cosmology. There are many, but this is considered one of the main puzzles, and it's the origin of matter-antimatter, because we know that observationally the antimatter that we see in the universe is compatible with secondary production. This means that it looks that at the beginning the universe was there is a big imbalance between the quantity of matter and antimatter, particular in this case here, baryons and antibaryons. So you can see that there is this weird number, and from inflation you can say, wow, wonderful, but I decided there was at the beginning of the universe there was this particular quantity of baryons, this particular quantity of antibaryons, and I'm happy. Well, you're not completely happy, because if you decide this number to be the boundary conditions of the beginning of the universe, well, at some point you had inflation, unless you find an alternative to inflation. And the inflation washes out completely the baryon asymmetry. So the point is that even if you accept that you had the initial conditions of with baryons, antibaryons giving this particular number, right? In the end, afterwards, you have inflation, and this destroys this number, puts that basically to zero, or many order of magnitude below this number. So the question is, how do we produce after inflation this number, and why this particular number and not a number of order 1, for instance? In general, there is a kind of theorem proving that the baryon asymmetry can be produced after inflation if you have 3 conditions. They are the so-called Sakharov conditions. You need baryon number violation, C and CP violation, and departure from thermal equilibrium. And this is the tricky and most interesting part, is that the standard model contains or almost contains these conditions. So you are almost able to explain the baryon asymmetry of the universe via features of the standard model, at least in principle. But then we see that technicalities forbid that. And now in 2 slides, we see that. So in the standard model, the B violation, the B number violation, is provided by some processes. You're sure that, well, mathematically and in quantum field theory, you're sure that they exist, the so-called Svalerons. Then you're sure that you have the Kabibo-Kobayashi-Mascava matrix that contains CP violation phases. So you have C and CP violation that is provided by the standard model. And the most important, the most important one for this talk is the first order phase transition. Because if the electroweak phase transition, the dynamics of the electroweak symmetry breaking proceeds via a first order phase transition, you have that the phase transition produces bubbles that expands, and nearby the bubble wall, you have that, and the bubble is moving fast, you are breaking thermal equilibrium. So the third Sakharov condition is satisfied. This general idea is so-called electroweak baryogenesis. And in principle, then we see that at quantitative level it fails, but in principle, the standard model or minimal variation of the standard model, we'll see that later, can explain the baryon asymmetry, but really in principle. So, but what it's crucial to obtain the phase transition. So, in 2 slides, why this phase transition is so important for electroweak baryogenesis. First of all, what first order for a phase transition? What is a first order phase transition? First order phase transition is, in the case of the Higgs, is a transition that occurs via tunnelings or thermal jumps from one phase, from one minimum to a different minimum of the potential. And what to expect? You have 2 kinds in the standard model in particle physics, at least naively. You have 2 kinds of phase transitions. In any case, you know that when you put the scalar fields in the thermal bath, you have this kind of term that dominates when the temperature is very high. This means that the profile of the potential is like that, this one. This means that the vacuum expectation value of this field will be 0. Then you decrease the temperature, and when the potential is this structure, you can see that what happens is that you start having a second minimum. At some point, the second minimum will be degenerate, and later on will be below the main one, the previous one, and separated by a barrier. This means that you don't have that the field automatically rolls from here to here. What you need is fluctuations of energy due to the thermal bath or quantum effects that allows the field here to escape from this and go here. And this is a tunneling on a thermal jump. So when it happens, since you have the barrier, you have production of bubbles where outside you have the original phase, the one where the vacuum expectation value of this field is 0. And inside you have that the vacuum expectation value of this field is different from 0. You have these bubbles. These bubbles represent the bubble profile here is the representation of the Higgs field. What you have is that in the profile of the bubble, right, you have that inside vacuum expectation value of the Higgs is high, then you have a variation, continuous variation, and outside 0, where the field moves from different from 0 to 0 is what you call the bubble wall. So this is a cartoon of a first order phase transition. And the sphaleron, what is a sphaleron? The sphaleron is an effect that destroys baryons and leptons, conserve their difference. But you can see that since leptons have a lepton number and they don't have a baryon number, and quarks have a baryon number but don't have a lepton number, you can see that since you are destroying quarks, you are modifying the baryon number. And this the contributions that is giving you the baryon violation, the B number violation. Then the picture of electroweak baryogenesis is that you have the bubble, right? You have the first order phase transition. Because of the first order phase transition, you have a bubble. And if you zoom on the bubble wall, this is the bubble wall, you see here inside you have the vacuum expectation value of the field is different from 0, outside is 0. And you have that due to the CP violation, you have an accumulation of antibaryons with respect to baryons in front of the bubble wall. This means since you have more antibaryons than baryons, this means that you will have more processes destroying antibaryons than those processes that are destroying baryons. This means that temporally you will have more baryons, the antibaryons. In this lapse time, what happens is also that the barrier is moving. So the baryon asymmetry that you have produced in front of the bubble goes inside. And in this way, you have temporarily at the moment an accumulation of a baryon asymmetry inside the bubble. And remember that the phase inside the bubble is the final phase of the universe. So what matters, what you would like to get here, is that the baryon asymmetry that you have produced here is not washed out. What do you need? What do you need to have this phase transition not to wash out? What you need that this phaleron inside the bubble wall is killed, is vanished, negligible. And how do you obtain that? Well, there are many technicalities, but the main point is that you want a phase transition to be very strong. When the phase transition is very strong, so you move from here to here, and this here has a background expectation value that is very large, these phalerons that in principle can destroy your baryon asymmetry is frozen. So its rate is suppressed. You can see here, this one is the phaleron rate outside the bubble, and here is the phaleron rate inside the bubble. If this here is the comparison with the Hubble rate. So in a universe that is expanding, you need this phaleron is active if its rate is larger than the Hubble time, the inverse of the Hubble time, and it's frozen if it's below the inverse of the Hubble time. So you can see from here that if the phase transition is first order but not strong, so the vacuum expectation value of the field after the phase transition is smaller than the temperature at which the tunneling occurs, you have that this phaleron is still active inside the bubble. And so it is active and washes out the baryon asymmetry that you have accumulated by means of the expansion of the wall. But if the phase transition is strong, this phaleron is frozen and the baryon asymmetry inside is maintained. Okay, wonderful. So in principle, we can see that here we have all the elements to explain the big puzzle of the universe, the baryon asymmetry. Now, the problem, there are two problems. First of all, here in this cartoon, I'm not stating the velocity of the bubble. And you can see here that we have many rates. And if this wall, for instance, is moving at the speed of light, probably the rates that I was describing are not fast enough to act and produce all the mechanisms. Basically, here you can see, right? You need that here in front. You have these phalerons that have the time to modify to destroy some baryons and to destroy some antibaryons. But you need a typical time scale to do that, right? And if this time scale is longer than the time scale at which the ball moves from here to here, very far away, well, these phalerons have the time to produce the baryon asymmetry. So what matters is that you need a first order phase transition that is strong, but also you need that the wall velocity is not huge. Okay, these are the ingredients for what we want to say about the baryon asymmetry. Please keep them, write it down because we come back later on. Then the stochastic background from first order phase transition. Dani explained you yesterday that for a first order phase transition, you produce a stochastic background. Very briefly, the idea is the following. You have, again, the first order phase transition. You have that, as in the same cartoon before, you decrease the temperature, and the profile of the field that is undergoing the phase transition has this kind of profile with a barrier. Then, at some point, You have the tunneling, and the tunneling produces bubbles. And as Danny explained you yesterday, when the bubbles move, in particular when they are close to collide on each other, they produce gravitational waves. And let me skip some concepts, right? Okay, here from what are the main characteristics of the phase transitions? So you have the bubbles that collide, and in principle, you want to understand the amount of gravitational waves that this bubble produce during the collisions. And what is the energy that is available? Well, the available energy is related to the latent heat of the phase transition. So roughly speaking, the latent heat is the difference in the vacuum energy between this minimum, the minimum outside the bubble, and this minimum, the value of the potential inside the bubble, outside the bubble. So outside, inside. And this quantity, so the latent heat, is measured by this alpha. What does it mean? That if alpha is very, very, very large, you have that there is a lot of energy. The energy gap between this phase and this phase is large. And this means that in principle, you have a lot of energy that can be converted into gravitational waves. So what you would like to have in principle is that, or what you expect is that larger the latent heat, the stronger is the gravitational wave signal. And you can see the main quantities that I've described, or that I'm going to describe now. The alpha, which is the normalized difference between the minima, basically, latent heat, and beta. Beta is telling you how many bubbles you have, in the sense that now imagine that you are at the nucleation temperature and you have that the first production of the first bubble. But then, of course, once this phenomenon is statistically permitted, you expect that here you have a production of a bubble, but in principle, you can also have here a production of bubbles. In particular, by the time the two bubbles collide, the universe will have cooled down a bit. And by cooling down a bit, this means that the profile is not anymore this one, but will be this one. So, and since the barrier here is very, very small, you will have very easily the tunneling producing the bubbles. This means that from this cartoon, you have that during the phase transition, you have production of many bubbles. And the faster this potential goes down, the larger larger number of bubbles you will have, because the rate is less and less suppressed. And in the end, the phase transition will occur via many, many bubbles. If you have many, many bubbles, you expect high frequency of collisions. And since Danny told you that collisions produce a gravitational wave signal, you expect that naively at least, that the higher the beta, the higher the frequency, the characteristic scale of the stochastic background, the gravitational waves that are produced by the process. So in principle, for a strong gravitational wave signal produced by first order phase transitions, what you would like is alpha large and beta over h. You normalize, you make this quantity adimensional, and you will like beta over h large as well, in order to have a frequency that is high enough. This is the expectation. And now, what do you have? Well, once you have these quantities, you have to go through multiple calculations and subtleties And you see that when I was saying that the gravitational waves are produced by when the bubble collide, was a naive concept. There are many contributions. And in general, you will see that you have three contributions. Danny explained them. And it is one is due to the bubble wall, this quantity. When the energy stored inside the bubble wall, when they collide, the bubble disappear, and you have energy that is released, and this energy can be converted into gravitational waves. Then you have the motion in the plasma, and you have the magnetic turbulence. And in general, you expect this kind of spectrum. This is the general predictions. And you can see that everybody is saying that the first phase transition is a kind of broken power law. But you can see that when you check the details, it's not always the case that it's just a kind of broken power law. For instance, in this particular case, you can see that if you consider the magnetic hydrodynamics effect to be large, what you have is that the bubble will have a peak, goes down, and then there will be even a secondary peak. Okay, so there are many subtleties and uncertainties. So, of course, it's an open research field, and it's required to shrink down the uncertainties on this signal. Then you can see the two main features of this signal. Let's focus for simplicity on this peak, the main peak. And for concreteness, we assume that this quantity, this contribution is negligible. In this case, you don't have the secondary peak. So let's focus on this peak, and we can see what happens to this peak. First of all, we can see that the frequency depends on the nucleation temperature, okay, but also beta over h. And why is it sensible to get that beta over h large means higher frequency? Well, it's sloppy explanation, but it's a naive explanation that is illustrative. You have that if this bubble, beta over h large means many bubbles, and as I told you, means that you have many small bubbles. They start small and they grow, and the collisions, you will have a high frequency of collisions. Then you have omega, the magnitude of the peak. And you can see that, okay, it depends on several quantities, but in particular, it depends on alpha. And alpha was, remember, the latent heat, the energy gap between the two phases. And you can see that if alpha is larger, the signal is stronger. If alpha goes to zero, if the two minima are almost degenerate, the signal will be very, very weak. And alpha strong means that in practice that the phase transition is also strong in the sense of electroweak baryogenesis. Because when you decrease a lot the potential, the two minima are also becoming more and more separated. So the quantities, summary of the quantities that enter in the prediction of the spectrum: alpha, beta over h, the nucleation temperature, in some extreme cases, the reheating temperature at the end of the phase transition, and this velocity, the velocity of at which the bubble is expanding. We saw that is crucial for electroweak baryogenesis, but here at the moment, I'm omitting, you can see here, the contribution of the effect of the velocity. Technically, there's some condition to estimate the velocity of the wall, at the velocity at which the bubble is expanding, but these are quite complex calculations and are really model dependent, so it's not trivial. But what I ask to you now is to do the following, right? So I say that I didn't give you the expression of the dependence of the peak on the velocity, but I ask you in the next 5 minutes to check and to see a bit. How do you do? I propose you to do that. Well, we have said that okay, the predictions are becoming more and more inaccurate. Of course, when you want to be precise, you have to include more technicalities. And in particular for this lecture, I didn't explain the details of the technicalities. But if you go to this page, the web page, you have a tool where you insert the quantities that are typical of the phase transitions. So the velocity, alpha, beta over h, the degrees of freedoms that your model has. 100 is the typical number for the standard model, and the temperature at which the phase transition occurs. 200 GeV. Electroweak scale is the typical case for electroweak phase transitions. And what I ask you, what I ask you is you go to this page was provided by the cosmology working group, but David was maintaining that. And what I propose you is now you go to this web page, please go, and you try these 3 sets of inputs. And please let me know the number of signal to noise ratio that you obtain, the signal to noise ratio that you, the signal to noise ratio value that you obtain in each of these cases. And roughly, I don't want the number, but try to check how omega peak is evolving, how the amplitude of the signal is varying. Okay, I give you 1 minute. I'm curious to see, because if all of you will try, I'm curious to see if the web page is robust enough to support so many people asking for some runnings simultaneously. And okay, please. Chiara, are you fine with waiting 1 minute?
Absolutely, absolutely. Let's see, I'm doing this myself.
Okay. And in the chat, you are invited to put the numbers that you obtain. Of course, the goal is to burn David's computer, right? So let's try to burn his computer.
So there is a question in the chat by Jacopo.
Yeah.
3 or 7 years for the duration.
3, please. Thanks, Jacopo. True. 3.
So Abigail has the SNR, the right one.
Yeah.
Regina as well. Well, the third case, I think the third case of Barry is not correct.
Okay, first of all, I can see that the computer is supporting, David's computer is supporting.
Matteo as well.
I rounded up my first case to 84.
The third case.
Oh, the third case.
Yes.
Maybe that's wrong.
Okay, now Barry has the right one for the third case. Diviarani has the right one for the first case. Okay, I think people got the point.
Okay, good. Yeah. So, good. So, and now, for those that for some reason didn't manage to obtain the result, these should be the results that you should have obtained. Unless I'm wrong. Eh? So, okay, so this was the prediction of the signal in the first case, this the second case, and this the third case. Okay, so first comment. You can see that the velocity is playing an important role, right? Because you are choosing this, all the parameters that I was discussing are the same, but the parameter that I was a bit overlooking is playing a crucial role. And as I told you, it's very difficult to determine that in a given model of particle physics. And you can see, okay, so you can see that it varies. And so the tricky part is that I told you, you keep note of that baryogenesis, electroweak baryogenesis, prefers slow wall velocities. At quantitative level, what does it mean slow? Well, means not 1, but 0.1 is low enough for those processes. So people that in some given setups were calculating the velocity of the bubble and were calculating the amount of baryogenesis that you obtain in, I remember the minimum supersymmetric standard model, right? Was this kind of number. I don't remember the precise number, maybe 0.2, 0.3. Okay? In this case, we were obtaining the correct baryon asymmetry by putting all the parameters at the correct value. But then, okay, you can see that here we have chosen a phase transition that is at these parameters that are very strong. This is indeed for large velocity. Here we are in units of c equal to 1. So here we are speaking about a velocity, a bubble wall that is expanding at the speed of light. If you, instead of putting 1, you put 0.99, you obtain the same result. So this is an important aspect, right? Because we have seen in this discussion that electroweak baryogenesis is helping you to obtain the baryon asymmetry. It's a good hint or a good reason for which, okay, we don't know what nature is doing, right? But if nature is doing that, electroweak baryogenesis, okay, and in this way, nature is producing baryosymmetry, this would be aesthetically nice, at least. And it's a mechanism that we can test because it's just electroweak scale. So wonderful. We would like that, right? But still, the baryon asymmetry requires a velocity that is not equal, super relativistic. And you can see, therefore, that there is a bit of tension between what you would like to detect, what you can detect, and what the kind of phase transition you would like for baryogenesis. Okay? I'm not saying that the tension is strong, but really depends on the particular model and the particular parameter space that you are exploring. In this case, where the phase transition, you are assuming that you have a model that is producing a very, 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 very strong phase transitions, and therefore a very, 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 very strong signal. Well, the price that you pay by reducing the velocity is not so terrible for the detection of the signal, unless you go to very small velocity. In this case, you are lost. Okay, so this maybe is the first take-home message of this lecture. Then I would like to stress something else. Here, this blue-gray region is the sensitivity of LISA, right? The one that you find in the proposals for the mission, for instance. And you can see that in this signal, for this signal that is super huge, the signal-to-noise ratio is 3,000 and something. Now, I would ask you to focus on this particular condition here, this particular scenario. You can see in this scenario that the signal-to-noise ratio is 200 and something, 300, but the signal is below the sensitivity curve. So, does anybody have an explanation of that? Naively, I would say if something is below the sensitivity curve on an instrument, it cannot have a huge signal-to-noise ratio. So understand that people are shy. So the point is that.
So Luis Longo is saying in the chat, integration time.
Okay, wonderful. Thank you very much. Yes, indeed. Right. The main advantage of the stochastic background is that it is there and remains there for the duration of the mission. In principle, in our lifetime, stay there forever, right? So this means that you integrate over time, and this is why you can obtain a signal-to-noise ratio that is huge, even if the signal looks to be below the sensitivity of the instrument. Okay. This is, of course, true for any signal that is not a transient signal. A signal that is there, it is not there, it appears and disappears. Like the binary events measured by LIGO. So the stochastic background has this feature, it's important. So, and this is why you would like a mission that stays there as long as possible. Okay, then now one second aspect of the stochastic background. The stochastic background is, in first approximation, is this kind of signal, right? So you can see that in the cases where the signal is strong, you have that the signal is not only well within the LISA sensitivity curve, but it goes quite close to other sensitivities. This one is the one of the Einstein telescopes. This one is for LIGO design, and this one is LIGO O2. And here you have the SKA, assuming a huge number of millisecond pulsars, a huge number of precise millisecond pulsars that you can measure. This case, in the case that we have 100, I guess this is more realistic. And this is the region of nanograph some years ago. Okay, this is a cartoon, so don't take it as a precise measurement. But what I want to show you here is that also for the stochastic background, you have the multi-band property. In principle, a signal that is well visible in LISA will be also visible, remember what we saw before, the sensitivity curve of the instrument is not giving immediately you if the signal is detectable or not in that particular instrument. You have to integrate over time. And as you can see here, these are the sensitivity curves of the parameter space of phase transition that different experiments can probe. In this case, in this plot, we are putting alpha, the parameter that is very large, is much larger than 1. So the plot becomes independent of alpha. We are assuming a velocity that is large, and okay, a number of degrees of freedom that is the one of the standard models, roughly. Okay. And then you can see that, so you have the parameter space that Einstein telescope can probe, the parameter space that a LIGO design can probe, the parameter space that in first approximation, current LIGO data and Virgo data are ruling down. And here, the region that, okay, this plot was done before the anomaly nanograph. So, and I prefer not to speak about this excess right now. So this is the region that if you took the 11 years data of nanograph and you trust them, this is the region that nanograph was excluding. And well, the main point in this plot is something that was related to the questions on cosmic strings yesterday, right? How can we test if, in the case of yesterday, the question was, how can I test the model of cosmic string if I have detection? And Danny was answering, okay, use the multi-band approach, basically. And you can see that also for phase transitions, you can use the multi-band approach. And this is important because you are not only detecting, proving that you have a stochastic background here and a stochastic background here, if you are able to detect such a background in both experiments. But you're also able to reconstruct the frequency dependent of the spectrum in one experiment and the others. And this is important because if you measure, let's take this line, right? Imagine that you measure very precisely in LISA this signal. Then are you very sure that the signal is going down with frequency with the slope? And because as we discussed in some slides before, we can have other features that can be relevant. And in particular, maybe the prediction that of the signal, the theoretical prediction, doesn't match the real signal. And from this mismatch, maybe we can learn a lot. And maybe what you can measure here, this mismatch is not in LISA, it's outside. Or if you measure the signal in Einstein telescopes, maybe you have a mismatch here. So it's important to have the global view of the signal. And the stochastic backgrounds allows to, the multi-band approach to the stochastic background allows us to do that.
Sorry, Germano, I'm interrupting a second. So it is now almost 1 hour that that you're talking, 55 minutes.
Okay, a couple of minutes more. I'm cutting.
Yeah. You do have definitely.
Okay.
Time more. I was just saying that it's about 55 minutes that you're speaking.
Yeah, and also Okay, thanks. So, and the same you can do with Cosmic Explorer, and you can see, okay, this a different plot. Chiara made that long ago, and you can see that if you are able to do a common analysis by joining the data, you gain a bit, because in this plot, what you have is that this is the region of signal to noise ratio 1 in LISA. This is the signal to noise ratio in the parameter space that Cosmic Explorer will measure with a signal to noise ratio larger than 10. And if you combine the data, you can see that the regions that you can explore are a bit bigger, right? This, the dashed line, is the standard ratio of the signal if you join the data. And of course, as I told you before, the advantage, at least from my point of view, is not only that the parameter space is a bit bigger if you manage to merge the data, but it's also important that you are testing different frequency regions of the signal. Then I guess that I want to skip something that I said. Okay, Danny, yes, I do a super summary of the rest that I was planning to say, and I just discussed a bit more in detail the final point. And we know that in the standard model, right, whatever I said till now is wonderful, but we were assuming a first order phase transition. And as Danny explained yesterday, in the standard model with the Higgs mass that is 125 GeV, the experimental one, you don't have a first order phase transition. You have a crossover technically, but this means that you don't have production of bubbles. And so whatever I've said till so far doesn't apply, because the assumption was I have a first order phase transition. So, but of course this means this has one advantage is that the search of the stochastic background with the power spectrum of the first order phase transition gives you a hint, a proof that we have particle physics beyond the standard model. And from the position of the peak, more or less, you know the energy scale of this new physics. In the case of LISA, LISA is probing the TV scale, and this is exactly the scale that also colliders and future colliders are probing. Of course, there is something that I consider interesting is that, well, what kind of model can be tested by LISA? What kind of models can be tested by the LHC? Models with the first order phase transition. And in particular, since the LHC, okay, we have more hope with the future circular collider to test something else, to find something, because so far LHC didn't find any strong deviation from the standard model, right? So everything is compatible with the standard model. So, but we hope that by the future circular collider that is testing a higher energy scale, we can find something. But still, LISA is flying to 1 decade. The future circular collider, not clear to me, but maybe it will be in the same decade. We are speaking about the 2030s, maybe late 2030s, depends on how, well, the economy of and the budget to this experiment. And I completely skipped what I want to tell you about particle physics, but please, the message is that you have models of particle physics that are also well motivated. So you're not building a model just to produce the signal, but you build a model because you want to solve fundamental problems in particle physics, and you check the phase transition and oh, it's the first order, and oh, it's testable at LISA. Okay, so this means that the science case of LISA for the first order phase transition is stronger. You're not building models that are testable, but you're building models. Okay, you're not building models because you want to have models that are testable, but you are building models because you want to solve some problems. And by the way, you have also that there is a signal in LISA. This is what makes some models a strong science case for LISA. And last comment is that these kind of reconstructions, because so far I've told you that some signals have a signal to noise ratio that is huge, but I didn't tell you if you can reconstruct the signal, because in principle, signal to noise ratio estimator is telling you that, fine, you have a stochastic background, but there might be many, as we saw at the beginning, there are many sources of stochastic background. You want to be sure, for instance, that the signal that you are detecting is not a foreground. If it is compatible for the foreground, well, you have not detected a primordial signal. And if you're testing, if your data are telling you that there is a primordial signal, well, which signal, which mechanism? And in order to disentangle one hypothesis from the other, what you need is a good reconstruction. And you can see in this forecast that under some assumptions, because performing this analysis in a real case by taking care of all the subtleties of Lisa is hard, it's not feasible now. But under some assumptions that are reasonable, you can see that a strong signal can be well detected. Here, okay, it's so small that, the uncertainty are so small, but here, what you have in this plot is you have the dashed line, right? The input signal, and this is. And around this line, you have also the error bars, the 1 sigma and 2 sigma region on the reconstruction of the signal. So you can see that where the signal is strong, you have that the uncertainties are tiny. And this means that if the signal is strong enough, you can reconstruct the signal with accuracies that are incredible. Okay. This is completely fake signal, and I don't expect that in nature. But you can see that even a signal, stochastic background signal, with weird features can be reconstructed with very high accuracy. And what matters here is that you're not, in this kind of analysis, you're not using a template to extract the signal. In this particular analysis, this analysis is agnostic. You know the noise of the instrument with some uncertainties, and you perform an analysis looking for a generic stochastic background. And this is the output. So again, there are some assumptions here, right? You are, in particular, the main assumptions are you are not taking into account the possibility of foregrounds in this case, but this is a good assumption when the signal is strong, because the foregrounds are not super used, right? They're relevant when the detection of the signal is borderline, so they are relevant, but they're not relevant when the signal is very strong. Second, here you're assuming that you have a good model of the noise of the detector, and okay, this is something that the community has to work on in the future. The third assumption is also that the data have no glitches, no instabilities. Here you are assuming, this analysis, you're assuming that the noise is Gaussian, right? So these are the main assumptions, but which are reasonable. So the message here is that, oh, wonderful, we can reconstruct the frequency shape of the signal with high accuracy when the signal is strong enough. So to conclude, what did we learn, or what did I explain today? Well, first of all, there are models that are well motivated, and these models are producing a first-order phase transition that is detectable at experiments like LISA. An extra good reason, partially linked, but linked with many subtleties, is that if you have first-order phase transition and you detect it, in principle, you have to work on the subtleties to understand if this first order phase transition is also the responsible for the baryon asymmetry of the universe. But of course, you have to check these subtleties, but the result would be wonderful. Moreover, I was a bit sloppy on that, but the prediction of the signal, the prediction on the stochastic background signal is becoming more and more precise. I didn't mention that, but 20 years ago, there was a prediction. And now we have simulations that takes years, or order 1 year, to run on supercomputers. And these simulations are starting telling us the feature, the small features of the signal. Of course, there are also theoretical uncertainties, but we hope to improve them in the future. Something that I consider very relevant is that if there is a signal, you can detect it with high accuracy, and you can reconstruct it with high accuracy. And this will allow us to understand the underlying physics. You have also the possibility of the multiband analysis, which are very nice if you want to be sure that besides, if you reconstruct the signal in a region, you know the signal just in that region. But knowing the signals at different frequency is important. And for many stochastic background signals, you have the possibility of testing the signal in more than one detector. And something that I didn't mention because I was running over that is that there is a synergy complementarity between gravitational wave detectors and collider detectors. And with that, I conclude. Thanks.
Okay, thank you very much. We do have, well, we won't, but we will take time for a few questions if there are any.
Ask one question.
Please go ahead.
Yeah, I'm sorry. I'm not in this field, so I'm completely just novice and learning this new cool physics. But just one question that I have is, you mentioned that the gravitational wave energy density as a function of frequency is well characterized for this first order transition, and you show this curve. And okay, so if it's a signal is strong enough, the LISA will detect that the gravitational wave stochastic background. But still, do we well understand all the astrophysical foreground contaminations that have the very distinct, the shapes that we can separate from the detection that we have, or still we need the more, the multi-frequency observations to completely understand the difference between these first, cosmological, background versus astrophysical background, the foreground.
Yeah. Yes. Okay. So, first of all, the prediction of the foregrounds at the moment is, at least in LISA, is rough. So, but typically, at least in first approximation, they look like a power law. So very first approximation, but of course, in the next years, we can predict this foreground with more accuracy. So now you have a foreground, and let's say this is foreground, a kind of power law signal that if you don't have a theoretical understanding of the prediction of the signals, can be interpreted also as, okay, from foreground, from the detection of the signal, if the signal is Gaussian, which is what happens for some foregrounds, and for sure, for most of the cases, also for the primordial stochastic background, right? You will have that the data, the signal that you measure, okay, is is the sum of the two, of the primordial signal and of the foreground. Now, the issue is that if you're able to reconstruct the signal even within the Lisa band, and this signal departs from your expectation of the foreground and is compatible also with your expectation of the primordial background, at that level, okay, you're quite confident that you're detecting the two. Of course, in order to disentangle the two, you need to be sure that you are reconstructing the two signals with high accuracy. And is it true? I think that this is true, but it depends on the particular scenario you consider. For instance, if you have the foreground here and the primordial signal is order of magnitudes below the foreground, you will not detect the stochastic background. If you have the stochastic, the primordial signal that is huge, and the foreground is order of magnitude below the primordial signal, you will reconstruct the primordial signal, but not the foreground. But given the frequency shape that are completely different, you will be able to understand that you are detecting a primordial background and not the foreground. And then you have the weird case, the borderline case, that you have the two signals are compatible with the same order of magnitude, right? And in this case, disentangling the two signals requires a good theoretical predictions of the foreground and of the stochastic, the primordial background, and theoretical uncertainties and experimental uncertainties. But you don't need the multiband unless you are in the borderline case. You don't need a multiband case, multiband approach to disentangle the signals.
Okay, thank you very much.
You're welcome.
Any other question? It doesn't look like so, but I wanted to add maybe to add something, which is the fact that there is one issue which is foreground, and there is another issue, I'm sure Germano agrees, which is knowing the noise level of the instrument. Yeah. This is also something that it is also a very necessary ingredient, because in some sense, signals, especially from the early universe, will just look as extra noise sources. So the problem is twofold. There is not only the astrophysical foreground, but there is also the noise of the instrument.
Yeah, I fully agree.
Okay, so if there are any comments or questions, then I thank very much Germano of coming here and giving this interdisciplinary seminar, really interdisciplinary. And we reconvene. Sorry, let me just stop the recording.